Hello everyone, welcome to the fifth week of sessions of NPTEL course Computational Process Design. So I am Dr. Hariprasad. So I'll be taking you through this journey from here onwards. So we would now started learning about heat exchanger design as the starting point. Then we will slowly move into the geometric design of reactors. Then afterwards we will go and study processes like how do we use the principles of sustainability in process design. I hope you are all ready to join with me in this journey. Okay, so today's session is all about how to design heat exchanger network. So of course, it says it is envisaged to conduct in two parts. So today we will go and cover about heat exchanger design network, heat exchanger network design first part, where we recall some of the basic principles of heat exchanger design. What are heat exchangers? And we talk about a concept known as composite curves, and we would conclude for today. And from in the second part of the heat exchanger network design, we start from composite curves, and we go a bit more into the detailed design of networks. For instance, we use principles known as pinch technology and so on. Okay, so just to give you the perspective, so we have around 5 textbooks kept as reference book for this particular course. So the material that I am going to deliver would mostly come from the reference number 2 and 3, which is conceptual design of chemical process by Douglas and chemical process design and integration by Smith. So the contents that I am going to cover, if you would like to go back and go through a find out a resource that requires larger coverage, kindly look at the reference number 2 and 3 for now. Okay, so let's get started. So we would just to give you the perspective, heat transfer is one of the most energy intensive process in a process industry. As a result, this is also one of that particular unit operations that consumes lot of energy and therefore cost. So it is important to have heat transfer heat transfer process in a chemical industry would be done in more economical manner. So as to achieve not only energy savings and also just to save economics and also to achieve sustainability. So just to recall what is heat transfer. Heat transfer is the transfer of energy from a warmer object to a cooler object, as we all know. As we all know, so if two bodies are in thermal equilibrium, there is no scope of heat transfer. We will only do the heat transfer when we have a warmer object and a cooler object in side by side. And again, just to give you the perspective, so there are 3 fundamental modes of heat transfer, as we all know. So as we all know, there are 3 fundamental modes of heat transfer: conduction, so which is the transfer of energy from a molecule to another by direct contact. And we know that the heat conduction equation that talks about uh, how the heat transfer is directly proportional to the temperature gradient, and and here if you see, Q conduction is equal to minus Ka delta T, and delta T here is the temperature gradient, okay, and K is the thermal conductivity, and Q is the heat transfer rate in the conduction, and of course A is the cross sectional area. So if you come to the next mode of heat transfer, which is of course convection. So convection is affected by is the movement of heat by a fluid. Okay, so while conduction is affected by a transfer of energy from one molecule to another, so convection require a fluid movement. For instance, this could be fluids such as water or air or anything that is under consideration. So now, the convection heat transfer, which we call it as heat transfer rate in the convection, which is Q convection, is actually is a function of 3 things. One is of course H, which is the convective heat transfer coefficient; A, the surface area of the heat transfer, and Ts is the surface temperature, and Tf is the fluid temperature. Why? Because that so you would have the heat transfer is typically affected by a fluid movement. So you need to have the the surface temperature where the heat transfer occurs and the fluid temperature that actually takes away the heat. Both has to be taken into the consideration. So H, the heat transfer coefficient H, and the area plays a key role. And if you look at even in all the three modes of heat transfer, see the critical bottleneck comes is the area, because you once we are in an industry and we are designing heat transfer equipments, or we are deploying heat transfer equipment, so the critical bottleneck that always one would be facing would be the space where you install the equipment, which is of course directly proportional to the area. So it is imperative that you, when you design an equipment, you should actually optimize the area so that you will be able to place them suitably. And the last mode of heat transfer, of course, is radiation. So it is the transfer of heat through the space by electromagnetic waves. So here the Q radiation, which is the radiative heat transfer, is function of emissivity epsilon, sigma, which is the Stefan Boltzmann constant, and of course the temperature of the of course A is the surface area and T is the temperature of the object, and T surround is the surrounding temperature. Unlike the first two modes of heat transfer, radiation heat transfer depending upon the fourth power of temperature. So when we are designing, even though there are three fundamental modes of heat transfer, when we design heat exchanger networks, so if you, what we would see predominantly is the effect of conduction and convection. So we would be using the principles of conduction and convection because while doing the heat transfer in a heat transfer equipment, we a hot fluid typically pass through over a cold fluid, which essentially indicating that there is a fluid movement. Okay, and hot or cold fluid would be inside certain tubes, so that would help, that would result in the heat transfer through direct contact, molecule by direct contact. So conduction and convection are the three modes, are the two modes that would be inactive when we design heat exchanger networks. Okay, so let's go into the detail of heat exchangers. Of course, what is heat exchanger? Heat exchanger is a device that transfer heat between two or more fluids. Okay, so device. So we are interested in or rather forcing heat transfer between two or more fluids. Of course, you can't make them in contact, because then the liquid would tend to be miscible if they react. So we wanted to have an equipment through we tend to pass through them independently, through which you effect that heat transfer. And there are various type of heat exchangers available, and in industries it is of course depending upon the type of fluid properties and the pressure in which you need to operate, temperature and flow rate. So you will have to select one among n options to select the best heat transfer equipment, which is of course the heat exchanger, depending upon the requirement that you have. The most widely used heat exchangers are shell and tube heat exchanger. In shell and tube heat exchangers, it would consist of a shell with bundles of tube inside. So we will see a schematic of that soon. So because all our analysis later, we are assuming that we do have a shell and tube heat exchangers, while the analysis the process of analysis will hold true for any type of heat exchangers. So shell and tube heat exchangers consist of a bundle of tubes placed inside a shell, and why it is so useful, it is because of its robustness and its agility, or its ability to handle high pressure. So typically the process fluids in a process industry, they typically would have very high pressure. So we will have to use an equipment that can withstand this operating pressure. So shell and tube heat exchange is one of that has its ability to withstand high pressures. So the other one is plate heat exchangers. Okay, plate heat exchangers are made of thin corrugated metal plates which are typically stacked together. And so see, the advantage of plate heat exchangers, typically the heat transfer efficiency is little on the higher side and it is fairly compact. So when you have applications wherein you require high heat transfer efficiency with a compact area, so you could definitely be able to choose plate heat exchangers. And the last, of course, there are many others. So I'm saying one such the third example that I would like to speak about is fin tube. In the tubes with fins typically increase the surface area, and eventually that would increase or improve the heat transfer efficiency. Tubes, the fins are the projections that on the tube which eventually increase the surface area of heat transfer. Just recall that all our heat transfer expressions that we have seen, be it conduction, be it convection, or even radiation, area is one of the key parameters that was that was part of the expression. So, yeah, so if you could just increase the heat surface area by adding fins, that would have eventually increase the rate of heat transfer. And what are the applications? So the heat transfer equipments find applications in many areas. For instance, industries such as power generation, even chemical processing, refineries, wherein even if you look at buildings, there are HVAC systems, refrigeration, and so on and so forth. So this is of course not an exhaustive list, and you tend to see most of their application in where you see that there is where you need to do a temperature gradient affected through which you need to do a heat transfer. So let's move on. So just just to kind of give you a brief idea of how shell and tube heat exchanger works. Okay, so this is a schematic of shell and tube heat exchangers. What you really see here is the shell. Okay, and there are tubes embedded inside it. Okay, and this you tend to pass the hot fluid or cold fluid in one of these tubes or in the shell, and through which the heat transfer takes place. Okay, so this shell is a large pressure vessels which you have kept a lot of tubes or rather tube bundles inside. Okay, so this is how it looks like, and how heat transfer happens. So when heat transfer occurs, when a fluid that flows through the tubes and another one fluid, the other fluid that we need to is part of the heat transfer process when it passed through the uh, pass outside the tubes but within the shell. So one of the fluid will pass through, of course, on the tubes and exit. The other fluid will pass through the outside the tubes, of course, through the shell. So you would see that there are areas in which they typically contact through the surfaces, and that would eventually result in heat transfer. And the tubes arrangements, so you can have, as I previously told, so there is these tubes are arranged in stacks. So there are various ways in which you could arrange this tube, and that is typically known as tube pitch. Okay, so there are so tubes are arranged in certain bundles, and you can't stack the tube together without spacing. Why? Because then there is no space for the shell fluid to pass through. So there would be some spacing, and there are certain standard patterns in which these tubes are arranged. For instance, triangular, square. Okay, and of course, just give me a minute. Triangular, square, and of course in the shape of a diamond, and so on and so forth. And this tubes will also influence the flow characteristics, because the fluid that is passing through the shell, which actually pass through this inside this tube pitches. And you typically install a material known as baffles. Okay, inside the tube. So what you can see over here, these are all the baffles. Okay, so you see, so what baffles will when incorporated in heat exchanger would result in. Okay, so it will direct the flow of fluid in a particular direction, that would be and thereby increasing the rate of heat transfer. Okay, so another application of baffle is that, okay, So, since if you are pumping in the fluid through the shell, and in order to avoid any vibrations of the tube, the baffle would I kind of act as a resistance. So, the first of all, the a baffle will help you to give a direction to the flow, and also it will also help the heat exchanger to withstand the high pressure flow. And when you install baffle, you would see that there are two types of flow that could happen, which essentially, so when if you install, so see, this is the baffle and the fluid cannot go inside, so it will actually pass through this would result in a flow known as cross flow. And once in, if you are here, okay, so between the baffle, so it will go in an axial flow. So these are the two flows that would result in when you install baffle in a shell and tube heat exchanger. Let's move on. So just again, just to kind of jog your memory again, so let's recall some of the typical flows that is used in heat exchanger design. Okay, so you can see the schematic here. The blue one typically indicates colder fluid, red one indicate hot fluid, and you this would so the placing the flow uh, in each other would typically result in three kind of configuration. So one is of course what we call it as counter flow, the other one is parallel flow, and the third one is cross flow. Okay, so let's understand each of this. The first one that you see over here is the counter flow. So which essentially mean that the cold fluid and the hot fluid are passing against each other. So direction of the cold fluid is is opposite to the direction of the uh, flow of the hot fluid. So they flow in, of course, in opposite direction, and this the advantage of such flow is this would increase the temperature gradient and thereby increasing the heat transfer. So if there are if you are wanted to achieve close temperature approaches, so counter flow is the most suitable flow pattern. So now the next type of flow is parallel flow, or it is also known as co-current flow. So so here what you can see, the both the fluids, you can see the red stream and the blue stream are in the same direction. So compared to counter flow, parallel flow, the temperature gradient that once you can achieve is much lesser, but as a result this operation of parallel flow is less efficient. The advantage of however comes is about its simplicity and what you call inexpensiveness to construct such parallel flow. So counter flows are of course is helpful to achieve better temperature gradient, but what I would say that so it is but affecting, or if you wanted to uh, uh, construct a counter flow in a heat exchanger, that is slightly more involved work compared to a parallel flow. The next class of flow is cross flow. So as we would really see here, the flows would be perpendicular to each other. So your uh, the fluid streams, which here it is indicated by the blue and red arrows, they tend to follow perpendicular to each other. So what you could see here, the advantage of cross flow is that it combines the features of both counter flow and parallel flow. Hmm? And it typically, and this is more difficult to achieve, but the advantage of cross flow is that where if your space is constrained, okay, so if you have space constraint because you need to install your heat exchanger equipment at a particular location, and where you need to have a constraint where you have a constraint of space, I think cross flow is a better choice. So now let's summarize each of the so let's kind of keep the keep a watch on how each of them perform each other. So let's start with counterflow. Counterflow has the highest efficiency and of course best for heat recovery, but difficult to kind of effect. And parallel flow, lowest efficiency and cost effective. And if you and also if you are if your heat transfer load or your requirement of heat transfer is not very demanding, parallel flow is a simple option. And cross flow actually, as I told, combines the counter flow and parallel flow advantages, and of course suitable for more compact designs. So now let's move on. So just again, let us look slightly in detail about what is happening inside a heat transfer equipment. This would help us to derive the expression for the heat transfer. Okay. So what you would see here is a cross-sectional area of the tube, and this is of course the tube wall. This is inside the tube, and this is of course outside the tube. Let R be denoted as the radius at any point inside the tube, and Ri is the inside dia and R naught is the outside dia. And if you need to get any delta thickness inside the tube, we use a notation called R plus dr. Okay. And what we could really see, so now you can see that from outside the tube wall, so this is of course the tube wall. Outside the tube wall, what you would really see is the shell side. Okay. And inside the tube wall, okay, this is inside the tube, and there are multiple resistance to the heat transfer. Okay. So multiple resistance inside in the sense that the heat transfer has the opposing effect of heat transfer. So what you would really see here is there would be a resistance at the shell side, and there would be a resistance inside and outside the tube. Okay. So that would be related to the so see, outside the tube here you would have a convection resistance, and inside the tube you would have a conduction resistance, and further inside you will have tube side convection resistance. So these are the three type of heat transfer resistance that that we need to overcome to effect the heat transfer. Now let's write the expression for heat transfer. Okay. So let's denote Q as the rate of heat transfer, and HS is the shell side heat transfer coefficient, A naught is the corresponding area, and delta is the temperature gradient inside the shell side. And so see, since it is convection driven heat transfer, we know that it is as a function of both heat transfer coefficient, area, and the temperature gradient. And of course, while writing this, we shall be able to isolate the delta Ts, which is the temperature gradient in the shell side, as Q divided by Hs times A naught. And now look at to the contributor factor number 2, where you have conduction. Okay. Conduction would require use of conduction equation. Q is the again the rate of heat transfer, K is the uh, conduction coefficient, area, and dt by dr. And of course the area here is 2 pi r l. So 2 pi r is the perimeter, and l denote the length of the tubes. So when we replace this, so when we keep a replaced by 2 pi r l, of course this the entire expression equation is a function of q q, k, r, l, and t. So now if you need to integrate, so if you need to integrate them and to identify to compute the total number of heat, to compute the total heat, what you can do is we could integrate this expression, fine, from R naught to Ri, okay, assuming that the temperature gradient that is affecting across the tube wall is Tw. Okay. So we use a variable separation and just do an integration between R naught to Ri, and let the temperature gradient that would be affecting due to that is delta Tw. Then we see that Q can be computed as 2 pi KL divided by ln R naught by Ri, okay, times delta Tw. And from this again we will be able to isolate your delta Tw back as Q divided by 2 pi KL divided by ln R naught divided by Ri, simple integration. So now coming to the third contributor, which is the tube side convection resistance. Okay. So again Q is the heat transfer, Ht is the heat transfer coefficient at the tube side. Okay. AI, and delta T delta T corresponding the temperature gradient inside the tube side. So, you can see that we are using the variable AI for the tube side area and A naught is for the shell side area, and again we will be able to isolate delta T, which is the temperature gradient in the tube side, as by rearranging by we will be able to find Q divided by HT AI. So now let's do the overall heat transfer. Let's go ahead and compute the overall heat transfer coefficient. Okay, the Q is of course U naught A naught into delta T, because and U, which is equal to UI AI delta T, because heat transfer across the uh, uh, tubes and the tube side and shell side should be fundamentally equal due to the energy conservation. And so delta T here is a combination of three things, which is delta Ts, delta Tw and delta Tt, which in these variables we have defined previously. So, which is corresponding to the delta T corresponding to the shell, corresponding to the wall, and delta T corresponding to the tubes. So, now we have the expression of delta Ts and delta Tw and delta T from the previous slide, and we just sum them up, and that would result in the total temperature gradient, which is delta T. Okay, so now that is available. If that expression is available, we can plug in that over here to get what to to get U naught, A naught, and delta T. So, you have the terms A naught and delta T, and the remaining terms which is coming as part of the uh, uh, which is a function of radius, and they would eventually contribute as the uh, overall heat transfer coefficient. What you could see over here is CQ is a function of UA delta T, and A and delta T are right here, and the any remaining terms that coming over here should be equal to U naught. So, what we should see here is that so this is under ideal circumstances. So, when a heat exchanger tend to operate and time progresses, and you would see that there are various type of fluid which we pass through the heat exchanger. So, as a result, what would happen is the tube wall would be fouled. Okay, so tube wall would be fouled in the sense that so there would be certain uh, fouling elements that actually stick upon the tube wall. As a result, heat transfer would be adversely affected. So, let us move on. So, now let us understand. So now let us further look into the how this temperature gradient has an influence on shell and tube heat exchanger. So, let us look at a simple shell and tube heat exchanger over here, wherein you pass in a cold fluid and eventually you would get get a cold fluid outside, and you would pass a hot fluid like this, and you would get a hot fluid outside. So, this is how this is how the arrangement that we are proposing. Okay, and what do we see here is that from the entry point of the hot fluid, the temperature of the hot fluid keep on decreasing. So, TH1 is the highest hot fluid of the temperature, and TH2 is the lowest hot fluid temperature, and TC1 is the initial entry or the low is the cold fluid entry temperature, and TC2 is the cold fluid exit temperature. Fine. So, now what we could do is let's compute Q in detail. So, let's see dt by dq. Of course, how do we compute? So, d delta t by dq. So, delta t here would be so delta. So, this is of course the slope of this particular line. So, d delta th minus delta tc would be computed as delta Th minus delta Tc, of course, divided by the total Q. So, this d delta T by dq would be computed as uh, delta Th delta Tc divided by the Q. And we all know that dq, of course, u a delta t, and so dq should be equal to u dA delta t. And so now now let's keep everything together. Fine. So delta Th by delta Tc divided by Q would be equal to d delta T divided by dq. So what is dq here? Is dq is u dA delta T, which again I would plug in. So now you can see that the differential variables only in this expression are a and delta t, dA and delta t. So we can integrate the area from 0 to a and integrate the temperature from delta Tc to delta Th. Again, simple integration. So you would see that, and isolating the q isolating the variables to q would result in u, okay, a times delta Th minus delta Tc divided by ln of delta Th minus delta Tc. So this particular term, which is resultant due to the integration, is known as logarithmic mean temperature difference. So if you are using this particular kind of an arrangement, so the overall heat transfer is a function of u, of course, which is the heat transfer coefficient A, and it is just not a delta T, but what we receive, what we get as the logarithmic mean of the temperature, which you could see that is the ratio of difference between delta Th minus delta Th and delta Tc, okay, and ln of delta Th divided by delta Tc. Fine. And if the fluids are isothermal, then the logarithmic this logarithmic mean temperature eventually become equal to the average temperature. So now we can see how the profile, how the fluid temperature variation happens when we have different types of heat exchangers. So let's start with a heat exchanger which is having counterflow. It is also written as one essentially mean that there is only one tube pass and one shell pass. So let's understand how the flow works here. The hot fluid comes in here and eventually pass through and exit like this, and cold fluid comes in this side and pass through like this and exit through this particular part of the heat exchanger. So the both the fluids are only passing one time each other, and this is how the temperature profile then looks like. Okay, hot fluid would keep on decreasing at Th1 to Th2, and cold fluid temperature would keep on increasing from Tc1 to Tc2. So the noteworthy thing here is that the Tc2 would be always higher than the Th2. So now what we can see here is the co-current flow. So which essentially mean that both the fluids are flowing in the same direction. So look at how Th1 flows here. Th1 comes inside, okay, go and exits, and Tc1 of course passing through the tube in the same direction and exit through through here with the temperature Tc2. And this is the plots are between the length of the heat exchanger and the temperature. So what you could see here is that the cold fluid temperature, of course, it will increase from Tc1 to Tc2, and hot fluid temperature would decrease from Th1 to Th2. And again, what we can see here, the Tc2 will be lesser than Th2, which is not the case here. So you can see the cold fluid temperature here would be higher than the hot fluid exit temperature in a counterflow. So the next type of pass, so here it is one pass, which essentially mean that the both the fluids are just passing only once through the shell. So now look at the case when you have 1-2 pass. So 1-2 pass here is essentially the first letter is always talking about the shell and second letter is talking about the tube. So 1-2 essentially meant that you have one shell pass and two tube pass. Okay. Okay, so now let's see how it works. So see the tube, this is the shell side fluid, it enters at TH1 and of course exit at TH2. Okay, and you can see the TC1 enters here. Okay, and it flows through this direction. Fine, and reaches here and actually takes a turn and goes in this direction. So the flow direction inside the tube is actually reversed, and first part is the flow is parallel to the direction of the hot fluid, and in the second part of course it is against, it is the flow direction is opposite to that of fluid. So this is typically known as partial counter current and partial co-current flow. And what you could see over here is TH1, again the temperature profile decreases from the entry temperature TH1 to TH2, and TC1 of course since it takes two paths and exit at the same place, you can see TC1 keep on increasing until one side reaches, then it takes a reversal and it goes back. Here also what you can see here is TC2 would be typically higher than TH2, of course on a smaller margin. So now let's understand what are the principles in allocating fluids inside tube and shell. How do we choose which fluid we should keep inside tube, which fluid should be kept in tube, which should be kept in shell. So typically expensive material, if you have expensive material, you keep this material through tubes. So of course this is of course to reduce cost and minimize the loss. So tube, when it pass through you, so there are minimal obstructions, so you would be able to save cost due to less wastage. So if you have anyway in heat exchanger you will have to work with two fluids. If one of the fluid has a tendency to fall, that should go inside tube side. In this case if this go to the shell side, it will destroy both the tubes as well. So what is happening? So if you have a fluid that tend to foul, if you pass it through the shell, of course the shell would be fouled, and also the tube outside part of the tube, external part of the tube will also be fouled. So in order to avoid that, we typically send those kind of fluids through tubes. The next, if the stream with higher pressure, it's better suited for tube sides, and the tube can efficiently contain high pressure due to the smaller diameter. If there are high pressure fluid, we prefer tube side flow. Again, allocating more viscous material to the shell side can result in higher heat transfer coefficient, assuming the flow would be remaining turbulent. And if you place a fluid with a low flow rate on the shell side, that would often allow for a higher heat transfer coefficient for that fluid, lending to more economical design. And the last, these are thumb rules. Of course, there are many other aspects that you need to consider, but these are some of the key points. Having hotter fluid inside the tube can reduce the shell surface temperature and potentially decreasing the need of insulation, and this is preferable due to safety reasons. So these are some of the thumb rules that one need to look for if you need to allocate which are the most suitable fluid inside the shell, and what is the most suitable fluid inside the tube. So now let's look at do certain analysis with respect to the heat exchanger. To proceed to that analysis, let's understand certain terms. Certain terms which is of course used universally. So what is a hot stream? Hot stream is a process stream that needs to be cooled, typically transferring its heat to the another fluid. Of course, cold fluid is a process stream that to be heated, which is usually gains heat from the another fluid. And And what is a utility stream? It is external resources used to heat or cool process streams within a heat exchanger network, such as steam for heating and cooling water for cooling. And what is heat recovery? Heat recovery is a process of reclaiming heat from processes or equipment and using it to preheat other streams, thereby reducing the overall energy consumption. So, what you need to understand that if you need to cool or heat a particular process, of course, the straightforward way is, if you wanted to heat, use a heater. If you wanted to cool, use a cooler. So then what are we doing? So you just use a heater and impart heat to the fluid, or use a cooler and take away the heat from the hot fluid. So by doing so, you are actually spending more energy. So but since heat recovery is an intermediate path. If there are two streams, one is of course to be cooled and one is of course to be heated, you identify them. Okay, you tend to kind of pass them through a heat exchanger. As a result, from the by using the heat exchanger equipment, you either preheat the colder stream, or you kind of cool the hot streams. So this entire process heat recovery. And what is heat load? The amount of heat energy that might be transferred or to a process stream to bring into the desired temperature. And another key important variable here is heat exchanger effectiveness. What is heat exchanger effectiveness? It is the ratio of the actual heat transfer to the maximum possible heat transfer under the same conditions. So indicating how effectively heat exchanger can perform under ideal conditions. So effectiveness epsilon is Q max by Q actual. So it is the actual possible heat transfer by it is the actual heat transfer to the maximum possible heat transfer, the ratio of the both of them. So now we use some of these terms in this in the subsequent part of the class, and in the next class in the while when we look at the network heat exchanger network design. So let's look at a simple case to understand why do we need heat exchanger and heat exchanger network. So consider this particular case. Okay, um, so you have a hot stream, and ideally you need to cool it down. The inlet temperature, which is represented Hi in is 373 Kelvin, and Th out is 343 Kelvin, and you need to typically impart around 200 kilowatt duty to effect this temperature change. And of course, if you have one option, use a cooler. So cooler would typically takes away all this heat. Look at the second case. You have a cold stream which is at a temperature of 283 Kelvin, and you need to take the temperature up to 333 Kelvin. Eventually, again imparting a heat duty of 200 Kelvin. So again, you can use a heater to effect that. But what you can see here, so see, you have 200 kilowatt cooling duty available, which you can actually use them to heat duty available, which you can actually transfer that to a cold stream, and thereby effecting a heat integration. This process of uh, reclaiming this process of reclaiming heat is known as heat integration. So look at the case here. So in heat exchanger, what are we trying to do? So you use this two things. So you take away the heater and the cooler, but we use the hot stream, which is at the 373 Kelvin, which is used to you pass through a heat exchanger, which is used to heat the cold stream, which is at the 283 Kelvin. So outlet of the hot stream would be lesser, because you transfer the heat from the hot stream to the cold stream, and it would be 343 as if it is expected. And you could just also so this would eventually increase, resulting in the increase of the cold stream temperature. So what are we? So this integration, what are we trying to achieve? The integration of heat exchanger eventually reduce the need of an external energy resource. So any hot stream of the process can transfer heat to any cold stream. So, we have to come up with an optimum flow stream to maximize the energy recovery. So, if you could optimize this entire process, this would result in a maximum energy recovery, thereby saving, thereby achieving savings in terms of energy, of course economics, and eventually lesser emissions, leading to overall sustainability. So, this heat recovery is typically can be represented by means of what is known as composite curve. Okay. So, consider a case where you have two streams available in a process industry. Okay. One is of course the cold, which is available at 40 degree, which is known as supply temperature, and you need to heat it to 110 degree C, which is the target temperature. And the delta H needed to achieve this is of course 14 megawatt, and the fluid heat capacity is let us say 0.2. And let us look at a hot stream which is available to is hot stream whose temperature to be brought down, which has the supply temperature of 160 and target temperature of 40. Fine. So, what we are going to do them, so of course you can pass them through a heat exchanger in a particular sequence, and this would result in the heat transfer. So, one thing that we need to look in this case, so you can plot how they can be integrated. Okay. So, you have the cold stream which is available, you are typically okay, yeah. So, your cold stream is available at 40, you need to increase its temperature to 110. You have your hot stream which is available. So, you can see the direction for cold, you have to increase it to 110. This is the direction of increase of heat or temperature. This is the direction of decrease of temperature. So, this is your 160 degree available is the supply temperature, and you need to bring it down to 40. Fine. At any, so if you want to effect the heat transfer at any enthalpy value, the hot stream would have the higher temperature, and this is of course the uh, and so you can see that the curve tend to have certain overlapping regions. So, this is the region wherein to have the overlap. Okay. And your red line, which is the hot line, is extending across the extending from the blue line, and of course, at this part of the curve, the blue line is also extending from the red line. So, this you would have, so the maximum possible heat transfer will happen only at this region of overlap. Okay. So, the heat recovery QEC, okay, so you need to effect a heat transfer of 14 megawatt. Okay. So, whenever there is the region of overlap is where you need to have the heat transfer. So, you could see that as the region of overlap increases, the heat recovery increases. Okay. And whatever is right here, okay, so the QH, and which is which is the region wherein your cold fluid extends from the hot fluid line, which is the minimum hot utility. Okay. And this side where the hot fluid line extends from the cold fluid line, which is known as minimum cold utility. So, QREC is what you can be affected by means of heat recovery, and for QH to happen, which is of course the hot utility, you need to supply externally, and QC you also need to take away from the system. So, as a result, what you can see, this delta T minimum. Okay. So, delta T minimum is the difference between the point the last point of the cold fluid and the point corresponding to which the hot fluid the difference between the temperature corresponding to that hot fluid. So, in this case, this is 10 degrees C. You can see that by changing the delta T minima, you can actually change the overlap. So, if let us say if this blue curve extends over here, so let us say if this blue curve extends over here, you can see that the delta T minima has got you could just change that. Now, the delta T minima is further smaller, okay, and the region of overlap got increased. Similarly, if you change this over here, you can see that overall coverage can be increased. So, what is the what are we trying to say here? Okay, if the delta T minima, if you can modulate, then you can actually change uh, uh, the level of heat transfer. Okay, so let's look at in this particular case. So this is the same example. What you can see over here, you can see that the cold fluid, hot fluid temperature decreasing, and this is the cold fluid temperature increasing, and this particular region wherein you have QH, you need to supply external steam, okay, to heat. So this is corresponding to 3 megawatt, for which you require an additional heat duty, and in this case the difference between so this particular range wherein your QC, which is corresponding to 1 megawatt, you require a cooler or a condenser. So what are we trying to say? So if you modulate this and if you cover, so if you could if you have the if you increase the coverage, you would see that the effect of cold utility and additional effect energy that you need to bring into effect, this would be reduced. So here by natural heat recovery you can get around 11 megawatt, and 3 you will have to supply externally, and 1 you have to take out additionally. So now let's assume a case wherein your delta T min is 20 degrees C, which is higher than that. You could visibly see that, okay, the coverage QREC will be much lesser. Here it is of course 11 megawatt, as the coverage is less, this area has been reduced, as a result QREC has become lesser. So which essentially mean that your QC would be higher and QH would be definitely higher. So these QH and QC you have to additionally supply. Only QREC can be reclaimed using heat recovery. So you can see that in this case, the outlet of the heat exchanger. So let's look at over here. So the so your heat exchanger, you need to yeah. So the outlet would be somewhere at 90 degree, and to make it to 110, you need to do an additional uh, operation, and similarly from 60 to 40. So eventually it stops at 60 and you need to bring it down to 40, you need to additionally require a cooler. So these and overall reclaimed heat recovery would be limited to 10 megawatt. So by manipulating the delta T min, you can increase the coverage and thereby minimizing the external additional cooling duty or heating duty that you need to additionally bring in to have the desired outlet temperature for the hot stream and desired outlet temperature for the cold stream. So this is so by so this so the way in which you could manipulate, I think that is what we are going to study at a later time, and this would result in the maximum energy efficiency. So I think so let's look at what is the effect of this delta T min. Okay, the smaller the delta T minimum, which essentially means that the of course increase the heat transfer area, leading to larger and more expensive heat exchanger. Reduced delta T min enhances the energy recovery, lowering the external and cooling need. Increased energy efficiency with smaller delta T min elevates the capital cost but reduces the operating cost. Higher delta T min cuts down the capital cost, but it can raise operating expenses due to less heat recovery. Very small delta T min may pose practical implementation challenges such as precise temperature control. And optimizing delta T min for energy recovery can significantly reduce the environmental cost. The optimal delta T min is a balance between energy efficiency, cost, and practical consideration. That is what we would like to achieve. Just to summarize, with this I think we would conclude today's session, and let's summarize the key points that we have learned. There are 3 modes of heat transfer: conduction, convection, and radiation. And next, heat exchangers are used to transfer heat from hot stream to cold stream effectively. Types of the fluids, their inlet, outlet temperatures, flow rate, and physical properties such as density, viscosity and thermal conductivity is even specific heat can affect the design and selection of heat exchanger. The heat duty, which is an amount of heat to be transferred, logarithmic mean temperature difference, and the heat transfer coefficient helps in deciding the flow arrangement. So, you need to actually pick one among that, among counter flow, parallel flow, or cross flow. So, these are the conditions that helps you to pick one among those, and of course, in determining the overall heat transfer area. Heat exchanger networks are designed to fulfill the heat load utilizing the heat from process streams, which are either cold or hot, by integrating them together. Efficient pairing of process stream to transfer heat, determining delta T, are the main focus in heat exchanger network design. So, with this concept, we will move into the next lecture. How do we use delta T minimum in a heat exchanger design, where we will now look into the where we actually look. So, here in this case, we only looked at one hot stream and one cold stream. We will look at more complicated cases of having more multiple streams. Okay. Then we speak about what is the pinch point and how to identify that, and how to do this the design in an optimal fashion. With this, I would like to thank you patiently listening it, and looking forward to see you again in the next class. Thank you.